March 31st, 2017. I printed this page out, the temperature principle of stellar evolution. I like the little calligraphy lines up there. I think it makes it look pretty cool. In this paper, it is explained that star surfaces cool as they evolve, therefore leading to a general principle of stellar evolution. The principle is as follows. The surface temperatures not impacted by outside bodies will drop as the star evolves. So you'll have a hot Jupiter maybe orbiting a really hot star really close, and it'll be about 1,000 Kelvin. But for the most part, that's irrelevant, because you move the hot Jupiter away from the host star, it'll cool down. Then you take the temperature and see how cool it is. Unfortunately, establishment, they screw the pooch multiple times. December 14th, 2014, you can find this edit on the Wikipedia page on the Harvard Spectral classification of stars, which essentially is called stellar classification. This part right here was removed. The three bottom lines. The L, T, and Y dwarf stars. I don't know if you can see that. Notice how the temperatures are really cold. 1300 Kelvin to 2400 Kelvin. 500 to 1300 Kelvin, and below 500 Kelvin. Those are where the planets are when they begin forming, obviously, the brown dwarfs, the gray dwarfs, and eventually the ocean worlds and whatnot. If you look at this a little bit more, you'll see that the radius becomes hazy. After M red dwarf stage, less than the radius of the sun. That sits at around 0.7, and then it gets all hazy. They have 0.08 and 0.15. So where's the 0.15 to whatever before 0.7? They don't ever mention that, because that's where the wrench gets thrown into the clockwork and starts to, mind my curse words, that starts to fuck things up royally. And if they would just realize that that's where they really fuck things up, they would maybe do something about it. And as well, with the luminosity, the bolometric luminosity is the total heat. I mean gamma rays, X-rays, visible light, infrared. So luminosity is right there. If you'll notice the luminosity, where's that at? Right here. Right there. And that cools down to, obviously, 0.08 luminosity of the sun. And then they go off the deep end, and they completely forget to describe what's between the M stage and the L stage. Clearly, that's where they really mess up, which is why they probably took it off the Wikipedia page. They don't want to confuse people. But my attitude is, instead of thinking you're going to confuse them, how about you let them see everything you got, and maybe they might make discoveries themselves. That's one of the biggest problems with establishment science these days. They think they're protecting people by keeping away the pseudoscientists and the cranks and the crackpots. No. If you want scientists to really learn, to really make something of themselves, throw out wrong ideas. Throw out ideas out there that are probably ridiculous. Let them think for themselves. Don't think that you're protecting them. You're just doing them a disservice. Because what happens in the future when these young kids, they grow up, they become adults themselves and professors themselves? What happens when they discover something? They're not going to know how to handle it. They're just going to go right back to what they were trained to do. Nothing's going to happen. That's why we're stuck in this situation. And another point on this, it says the Harvard Spectral classification is a one-dimensional classification scheme using single letters. Main sequence stars vary in surface temperature from approximately 2,000 to 50,000 Kelvin. Now, I can demolish the main sequence stuff really easily. Stars cool well below 2,000 Kelvin all the way to, near 0 Kelvin. So what happens between 0 Kelvin and 2,000 Kelvin? Why isn't there any distinguishing characteristics between those stars? This is basic thermodynamics. If something's hot, it's going to cool down all the way until it loses all of its energy. yet it's not mentioned. It shows that the surface temperature delineation of between 2400 and below, or 2000 and below, was ad hoc. They added it on there. The reason why they added it on there, because they never seen a star by definition which was colder than 2000 or 2400 Kelvin. So they said, well, if it doesn't have a spectrum, then it's not a star, it's a planet. Little do they know it's an evolved star. So we can completely throw out the concept of main sequence, which means we can also, on that note, throw out the concept of fusion inside of stars. There's something else going on there. There are plasma feedback loops. There's incredibly magnetic, energetic events that are happening on stars. Electromagnetohydrodynamics is how stars, that's how they work. This whole fusion stuff was in the 1950s, and we seem to been still obsessing over it. Unfortunately, that's not the path we're going to take. If they do want to study fusion, they should study active galactic nucleuses. That's where any type of matter creation process is happening. The central energetic core of the galaxy shoots out material in bilateral configurations. That's where matter is being created by supposed fusion reactions and other types of reactions. Not inside of stars. Stars are electrochemical, thermochemical, and mechanical processes. They're very, very dull, and they are very, very stable. And fusion isn't a stable. Fusion isn't a stable process. Fusion is incredibly violent and energetic. Good thing. It's a good thing the sun is stable, or else we wouldn't have life here. But I think I made this video long enough. Oh yeah. One last note. The fraction of main sequence stars, or their terms of main sequence, if you look at that part right there, you'll notice it'll have 0.000003%, which is a very, very small fraction of stars, and you have 0.12, 0.13, and then 0.6, then 3%, all the way down to 7.6, 12.1, 76.45, I think that is. I'm reading it backwards here. That means there's huge percentages of these very evolved stars in the bottom. They think they wanted to make it complete with 100% right here, and then ignore all the other evolved stars. Well, they have a lot of work to do. But, alright y'all. I think that sums up this talk. Hopefully, Baz, you can make something of this. Maybe a new video or something. Alright, later.